The last section provided an intuitive understanding of what word vectors are, but I haven't yet disclosed how words get assigned a particular location in an n-dimensional vector space. Let's return to that quote from J.R. Firth in 1957. "You shall know a word by the company it keeps." What that means is that a word's meaning can be very well represented as the average of its neighbors. Let's look at some key word vector papers that brought us to the great position we're in with deep learning for natural language processing today. Famed psychologist David Rumelhart and illustrious deep learning pioneer Geoff Hinton published perhaps the first paper involving neural network learned word representations in the journal Nature in 1986. Yoshua Bengio and his colleagues at the Université de Montréal published the first modern paper on directly learning distributed representations of words, that is, word vectors, in 2003, though this paper was not particularly well known in its day. At the International Conference on Machine Learning in 2008, Ronan Colobert and Jason Weston revised the concept of learning word vectors with deep neural networks introduced by Bengio et al. 5 years earlier. 5 years after that, in 2013, in the Proceedings of Neural Information Processing Systems, or NIPS, the most important annual conference on neural networks, Thomas Mikolov and his colleagues from Jeffrey Dean's lab at Google headquarters in Mountain View, California, published their word2vec method for converting natural language into distributed word vector representations. Word2vec is both simpler and more efficient than the previous approaches. It merits writing it out right now, as we will be working with word2vec a fair bit in these live lessons. It is the predominant method today for embedding words in vector space. The last paper that I want to talk about here is the leading alternative to word2vec, which is GLOVE, Global Vectors for Word Representation. Like word2vec, GLOVE is an efficient algorithm for creating word vectors from a corpus of natural language. It was introduced by Jeffrey Pennington, Richard Socher, and Christopher Manning, who were colleagues at Stanford University at the time, in 2014. Word2vec and GLOVE differ in their underlying methodology. Word2vec is predictive, while GLOVE is count-based. You can check out the respective papers for details. Both produce vector space embeddings of words that ultimately perform similarly in downstream NLP applications. One advantage of GLOVE is that it was designed to be parallelized over multiple processors or machines. So it might be the better option for you if you're looking to create a vector space with a very, very large corpus with many unique words. In these live lessons, we're working with natural language datasets small enough that you can comfortably develop your NLP skills on a single local machine, so we can safely stick with word2vec, which has more implementations available and is more widely used. All right, so let's get into a little bit of detail. We won't get into the mathematics, but we'll develop an intuitive understanding of how word2vec works by working with this little phrase here, deep learning for natural language processing. Have you heard those words enough yet? So word2vec is an unsupervised learning technique. That is, it works on a corpus of natural language without making use of any labels of the data if these labels happen to exist. A corpus is just a large set of natural language, a whole bunch of documents. Because it is an unsupervised technique, this means that any natural language dataset can be used as an input to the word2vec algorithm. When running word2vec, you can choose one of two underlying word2vec architectures, which will result in comparable results despite maximizing the probabilities in opposite ways. Let's consider the passage of text on a whiteboard as a silly example. So let's say that our target word in this sentence, and I'll explain what that means in a second, is natural. So this is our target word, and the words around it are context words. So if we have a window size, if we assign a window size of 2 to our context words, that means that the 2 words to each side of the target word are considered the context words. So these are context words, and so are these. If we set a window size of 2, we nearly always have symmetrical window sizes on both sides, so that would mean that we have 4 context words in total. At the beginning and ending of a document in a corpus of data, we use padding, so characters that, or markers that don't represent any meaningful words, so that the first word in a document would have 2 padding characters to the left of it, and the final word has 2 padding characters to the right. We'll cover this in more detail when we apply word2vec later. So I talked about 2 architectures for getting at the same problem that work in opposite ways. The first one is the skipgram architecture. Skipgram. So what it does is it predicts the context words given the target word in the middle. In more technical machine learning terms, the objective function or cost function for the skipgrams algorithm is maximizing the log probability of any possible context word from our data set, from the whole corpus, given the current target word. The second architecture is continuous bag of words, SIBO. The SIBO architecture predicts the target word from the bag of all context words. So it's the inverse. Again, in the technical machine learning language we used for skipgram, the objective function for the SIBO algorithm is maximizing the log probability of any possible target word from our data set given the current context words. The target word in SIBO is predicted to be the average of all the context words considered jointly. Context word position isn't taken into consideration. So whether it occurs here or here or here or here doesn't factor into the algorithm. Nor whether the word is before or after. It's all equal. That the SIBO approach has that attribute is right there in its name, bag of words. You can imagine taking all the context words within the window size, so learning for language processing, bagging them up. You can think of even shaking up the bag. The sequence of words is totally irrelevant after you do that. We simply calculate the average of all of those context words shaken up together. After considering the intuitiveness of the bag of words moniker, how about the C, the continuous part of the name? Here too lies insight into how the word2vec function operates. Word2vec passes over each of the words in the corpus, continuously creating bags of words around it. So if we were worried about syntax, the grammar of a language, where word order does matter, then that would be an issue. But since with creating these vector space embeddings, we're only worried about semantics, the meaning of words, it turns out that the ordering of the context words is irrelevant. I put together this summary slide here to summarize the word2vec architectures, the 2 different options we have. So the skipgram architecture predicts context given a target word, and the continuous bag of words, or SIBO architecture, predicts a target given context words. Some of the relative strengths, the key relative strengths of the skipgram architecture are that it is slightly better for small data sets, and it represents rare words a little bit better. On the other hand, the continuous bag of words algorithm is many times faster, so is more useful for large data sets, and it has a slightly better representation for frequent words. An additional little complication with word2vec is that in addition to these two architectures, there are two efficient training methods. The first one is called hierarchical softmax, which is normalized and is itself better suited to rare words. The second one is called negative sampling, which isn't normalized and is better suited to common words and to low-dimensional vectors. For our purposes in these live lessons, we don't need to get into the nitty-gritty of the differences between those two algorithms. They perform similarly enough for us. So after applying whichever architecture, skipgrams or SIBO, and which of the two algorithms that you selected between, the word2vec algorithm output consists of the n-dimensional word vectors we became familiar with earlier. So if you imagine that we had a 3-dimensional space, though it could have been 25 or 300 or 1,000 dimensions, so we'll have a dimension representing each of the 3 dimensions in our n-dimensional space, so these are 3 columns, and then for each of our words or tokens in our dictionary, so deep ends up being a word in our dictionary, learning ends up being a word in our dictionary, and the word2vec algorithm learned based on the context words around this given target word throughout our gigantic corpus. We end up with a particular coordinate in the 3-dimensional space representing the word. So it could be positive 0.42 for x and 0.67 for y. I'm just making up numbers here. And similarly, all of your words end up with a particular coordinate in that 3-dimensional or that n-dimensional space. Another key point regarding the word2vec algorithm is that we train our model using stochastic gradient descent. Our data set would nearly always be too large to fit in memory and perform gradient descent on all of the words and windows. Instead, we typically update our model parameters after passing over every single individual window. So our mini batch size is equal to 1. If you're looking for details of word2vec mathematics, I recommend checking out the CS224N Lecture 2 out of Stanford University in 2017. It would take too long to cover the details in these live lessons, and while understanding these details is good practice, we don't need any understanding of word2vec's underlying mathematics to apply the technique effectively in natural language processing applications. When we are evaluating the word vectors we've created, so we had our natural language corpus, we chose one of the two architectures, we chose from one of the two algorithms, and then we converted all of our words into a vector space of n dimensions. And how do we evaluate the quality of these word vectors? So we can evaluate them intrinsically or extrinsically. These are the two broad perspectives for evaluating word vector quality. Let's talk about intrinsic first. So intrinsic evaluation is evaluation of the word vectors not on your final NLP application like sentiment analysis, but its performance on some specific intermediate subtask. This could be, for example, the assessment of your word vectors on some objective evaluation metric, like a word vector analogies database, or assessing the word similarity scores of synonyms. Intrinsic evaluations are quick. They may help you understand intermediate steps in your NLP applications. However, these intrinsic evaluations will not ultimately be helpful to your NLP application unless you've identified a real quantifiable relationship, some kind of correlation between performance on the intermediate test and your final downstream NLP task. Now let's talk about the extrinsic evaluation. So this is evaluation of word vectors on your real-world downstream NLP application, like sentiment analysis or named entity recognition. In these live lessons, we'll use extrinsic evaluations only. While it can take longer to evaluate because we have to carry out all of your subsequent downstream steps in our code, including an often complex deep learning model, we can be confident that a change to our word vectors is worthwhile retaining if they make an appreciable improvement in the accuracy of our final NLP task. We'll go over hyperparameter tuning for deep learning natural language processing models more comprehensively later in these live lessons, but there are already a number of hyperparameters to go over for whenever you're evaluating your word vectors. The key ones are the number of dimensions. So larger will be better up to a point, perhaps several hundred, but then the improvements will drop off. The second thing is window size. A good starting point for the skipgrams architecture is a window size of 10. For the continuous bag of words architecture, a good starting point for your window size is 5, and you can vary a little bit around either of those to optimize. The number of iterations of training your word2vec algorithm will make a difference. Like the number of dimensions, more tends to be better, but again, only up to a point. The fourth thing is dataset size. Unsurprisingly, having more high-quality natural language data that are relevant to your task is better if you can get it. Cool. Now we have an intuitive understanding of what word vectors are and how to create them. Up next is how to find natural language data for feeding into NLP algorithms like word2vec, which we'll get to right after that.